Welcome to solverfy.
Let's find the pH of these four solutions. An important thing to remember is that NaClO dissociates completely in water into Na plus and ClO minus. And if we have a certain concentration of NaClO, let's say a random 0.5 molar, this will imply the same concentration of Na plus and ClO minus. So in this first solution, since we have 0.1 molar of NaClO, this means we also have 0.1 molar of just ClO minus. For solutions A, B, and C, since HClO and ClO minus are a conjugate pair, we can use the Henderson-Hasselbalch equation to solve for the pH. Hypochlorous acid, HClO, has a Ka value of 2.9 times 10 to the negative 8th. pKa equals the negative log of Ka. So hypochlorous acid has a pKa of, let's find the 7.538. So for part A, the pH is equal to 7.538 plus the log of the concentration of ClO minus, which is 0.1 molar, over the concentration of HClO, which is also 0.1 molar. So this is equal to 7.538 plus the log of 1, or just 7.538. For part B, the pH is still 7.538 for the pKa, plus the log of 0.15 over 0.1, which is equal to 7.714. And for part C, the pH is again 7.538 plus the log of 0.1 over 0.15, and this is equal to 7.362. Notice that when the concentrations of acid and base are equal, as in part A, then the pH is equal to the pKa. If we have more base than we have acid, as in part B, then the pH is higher than the pKa. And if we have more acid than we have base, as in part C, then the pH is lower than the pKa. In part D, we're adding sodium hydroxide to the solution in part A. So the hydroxide ions from the sodium hydroxide will react with the weak acid to form water and conjugate base. And now we can create an ICF table. So initially we know we start with 0.005 moles of hydroxide ions, since we have 0.005 moles of sodium hydroxide. And now we have to figure out how many moles of hydrochlorous acid and sodium chloride we begin with, because we have the concentration, but we need it in moles for the table. Molarity equals moles over liters. So moles equals molarity times liters. So for each, since the molarity is equal, 0.1 molar for HClO and 0.1 molar for NaClO. And also the liters are equal since we're using 1 liter of the solution. We can find the number of moles of each just by doing one calculation. So number of moles is equal to 0.1 times 1.0, or 0.1 moles for each. So we can add that to the table. We have 0.1 moles of HClO initially, and 0.1 moles of ClO minus initially. And liquids aren't included in these calculations, so we can just ignore water here. Now, since this is a complete forward reaction, we know that everything on the reactant side will react if it can. And since hydroxide is the limiting reagent, we react all of that. So for change, we have minus 0.005 moles for hydroxide. And since there is a 1-to-1 ratio of hydroxide to HClO, we also have a change of minus 0.005 moles for HClO. And again, there's a 1-to-1 ratio of hydroxide to ClO minus. So we have a plus 0.005 mole change for HClO minus. For the final amount, we just add the initial and the change. So for hydroxide, we end with 0 moles. For HClO, we end with 0.095 moles. And for ClO minus, we end with 0.105 moles. This is in a 1 liter solution, so we end with 0.105 molar ClO minus and 0.095 molar HClO. And now that we have our final concentrations, we can use the Henderson-Hasselbalch equation again to find the final pH. So the pH is equal to the pKa, which is 7.538, plus the log of the concentration of ClO minus, which is 0.105, over the concentration of HClO, which is 0.095. This means our final pH is 7.581.